So welcome here, last day, and so today I'm just going to kind of review, maybe go through the chapters and kind of talk about the main stuff out of those chapters, and that was sort of the game plan. So nothing too formal, sort of planned here. But before I do that, is there more specifically any topics or anything like that you would like me to kind of go over more specifically? Or if not, again, we'll just start at the beginning and kind of roll through the chapters. Anything specifically anybody would like to talk about or anything? No? Okay. Then why don't we do that? We'll just start way back when. Yeah, so I suppose 15, 16 weeks ago. So we opened up this class, really. Hitting sort of chapter kind of 1 and 2 comboed together there. And I believe chapter 1 and 2, it really was chapter 1 was sort of an introduction to chemistry. We talked a little bit about the scientific method and all that, but really chapter 2 had the most sort of stuff that we did discuss. So in chapter 2, we obviously talked about things like measurements. And when you take a measurement, as we've talked about, there's always some degree of uncertainty with a measurement. So again, the kind of classic so if we had a sort of line there and we were going to measure it, we would count the little markings 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There's obviously 10 markings in between 1 centimeter, which means in this case, each one is 0.1 centimeters. That means if we look at it, it is at least 1.1, 1.2, 1.3, and 1.4 in this case. As we talked about, it's obviously not exactly 1.4, so there's where the degree of estimation comes in. And typically speaking, we could usually go one more place to the right of that smallest marking. And in this case, maybe we call it a 5. And this would be, again, a proper measurement where we record all the certain numbers plus that first uncertain number. And if you remember, this is really what makes up significant figures, right? Is that type of measurement where you record all those guys. We also talked about, obviously, how to count significant figures. All zeros, all non-zeros are significant. When we talk about zeros, there's a few different types. Any leading zero is not significant. So that would be anything like 0.0001111. All those zeros are not significant. A reminder again, we don't start counting obviously until we hit the first non-significant or first significant figure there. Trapped zeros are significant. So those are zeros once again between two numbers. Those would be significant, and zeros at the end are significant if there is a decimal place. So again, if you had 400.0, all those zeros would be significant because of the decimal place. If you had, say, 400 as a measurement there, it would not be significant. So this guy would have 1 sig fig, and this guy would have 4 significant figures at that point. More importantly, and as we use probably for a lot of our chapters in terms of significant figures, is really calculations involving significant figures. We also talked about there in chapter 2. And remember that when we multiply or divide, we do look at the sig figs, and the answer is the same as the number with the smallest sig figs. So, if we took 4.2 times 1.30, we should end up with 2 significant figures based off of that number there. Remember, though, that when we add and subtract, it is a little bit different. We're looking actually at decimal places. So the answer should have the same number of decimal places as the smallest number of decimal places. So if we took 4.1 plus 2.00 and we add that together, that is 6.10. In this case, we would take it to 1 decimal place because of that, and we would just call it 6.1, which obviously has 1 decimal place, but 2 significant figures. Any questions on sig figs measurements? Hopefully we still remember all that, I suppose. Yeah, so yeah. So it sort of depends. The general rule is if you're doing sort of multiple calculations kind of in a row, you probably would not want to round to the very end, but you wouldn't want to keep track of your significant figures. So that's usually the best practice. We also talk about rounding in this chapter. And again, if you are going to sort of take an answer and then kind of do another calculation and then take an answer, do another calculation, you definitely don't want to round too much along the way because it'll move you sort of further and further away from the correct answer. So the general rule is you just kind of want to keep track of everything that you did and then sort of probably clean it up at the end would be probably the best move in terms of the calculation. Yeah. Other questions on that? Okay, so lastly, I think in this chapter here, and as Mark was talking about there, again, what we're talking about, if you're doing multiple sort of steps there, and then maybe, obviously we would do this part first and we want to keep track of our sig figs and then do this part next. But again, I wouldn't probably round until sort of the very end there. The last thing we sort of talked about in this chapter, really of importance, was obviously density. And density is mass divided by volume. And remember that we could rearrange this guy in several different ways, or a couple other different ways. We could solve for volume, which would be mass divided by density. And we could solve for the mass, that would be volume times the density. We talked about the DMV triangle, I think. And again, that's a way you can remember that. So obviously units of density are usually grams per milliliter or grams per cubic centimeter when we're typically dealing with solids or liquids. And if you remember that a milliliter is really the same as a cubic centimeter, they are a one-to-one relationship. When we do take a volume or 3 length measurements sort of and times them together, that is how we get to something like cubic centimeters. If this was the length times the width times the height, and that would be a volume. Obviously, we could also take a direct reading. And obviously, when we take the reading, we want to read from the bottom of the meniscus. And really, the third way we talked about sort of the volume here, especially with density, is volume by displacement. And obviously, volume by displacement is when we take a liquid like water and we take any type of solid object basically and dump it in there. What is going to happen is the volume there of that liquid will rise with the object in there. And we have an initial volume and a final volume. And if we want to find the volume of that object, we simply take the difference of those two. So the volume of the object would be the final minus the initial. And that's a very, very common way in density to figure out the volume of an object, is basically just to submerge it in a liquid. Any questions on density there? Yeah. So obviously, if something is more dense than water, right, it will sink, right? And if something obviously is less dense than water, it will float, right? Now, I guess I did skip a kind of a big topic in this chapter, which was obviously dimensional analysis, conversions, and and doing those type of calculations. So let's just review that again, just to make sure. We did talk about dimensional analysis in this chapter. And that is a process where we really use equalities, like 12 inches is 1 foot. And we could write conversion factors for that, which are, again, just fractions, where we could obviously say 12 inches over 1 foot, or 1 foot over 12 inches. And when we work out these problems, as we talked about, to show sort of the units canceling, it's always opposites cancel. So obviously, if you had 4 feet, you want to know how many inches that would be. Feet are up on top, so foot would go on the bottom. 12 inches would go up on top. Again, the feet here would cancel. We would end up with 48 inches as our answer here. Now, when we do these things, remember that for the most part, all these equalities are what are considered exact numbers. And an exact number is basically one of two things. It's either a definition like that, 1 foot is equal to 12 inches, or it is something that is counted. The importance of exact numbers is we do not look at them when we're doing sort of calculations in terms of significant figures. The one place where a conversion will not be really a exact number is if you cross over from metric to English conversions, right? Those you should technically look at the significant figures in the conversion factor there, except, if you had something like 1 inch is 2.54 centimeters, that's an exact conversion, so you don't have to worry about that. But all other sort of English to metric sort of conversions, you technically should look at the significant figures in the conversion factor. In most cases, it's still usually will revert back to that original number in terms of significant figures is probably the right one you should end up with, but you should look at them. If you have an English to English conversion, you're good. You don't have to worry about it. It's an exact. And obviously, if you have a metric to metric sort of conversion, you don't have to worry about that as well. Question on dimensional analysis, conversion factors. Don't forget as well, we also talked about the very common mistake that people make when they go use the prefixes, right? Like kilo is 10 to the 3. So for example, that would mean that in 1 kilogram, there are 10 to the 3 grams. So it's very common. Reversal people do a lot and get those incorrect. So when you see those prefixes, that is how much there is in the base unit to one of the prefix units. And again, that's a very common, as we talked about, that people sort of reverse those things. Any question on anything out of really chapter 2, conversions, dimensional analysis, density, significant figures? Then after chapter 2 there, we roll to chapter 3, I think. And in chapter 3, we talked about really matter, I believe. And we talked about the different states of matter. So obviously there is solid, where things are obviously typically packed in there pretty tight to one another. We then have liquid, where they are still relatively packed in tight to each other, but again, a little bit more room for movement, which is why liquids are fluid. And then obviously we have the gas phase, where everybody has basically broken apart from one another or flying around. We also talked about the transitions that occur as you go from one state to the next. So as we go from solid to liquid, that's the process of melting. Going the opposite way, liquid back to solid, is the process of freezing. Going from liquid to gas, that's the process of evaporation or vaporization. Heading from gas back to liquid, that is condensation. Going from solid, skipping the liquid part, to the gas, that is what is known as sublimation. heading from gas, also skipping the liquid part and going back to solid. That is deposition. We also talked about the idea that these processes really do occur at the same temperature. So our process of melting and freezing occur at the same temperature. And that's the normal melting point or freezing point of a substance. Also evaporation and or vaporization and condensation also occur at the same temperature. And that is where the normal boiling point of a substance basically occurs. So for water, obviously that's 0 degrees for our freezing point and 100 degrees Celsius there for our boiling point. It really, when we were at exactly those degrees Celsius or temperatures, right, we have basically both phases in equilibrium with each other. So at 0 degrees Celsius, we got ice and liquid water. When we're talking about water, again, not to get a little bit above or below that 0, that you sort of fully transition to the next phase. And obviously same thing at 100 degrees, we got kind of steam and liquid water in the case of water. And again, not above or below there 100 that you really transition into the new ones. What really matters in this case is energy. And as we go from solid to liquid to gas, those are all processes that require energy to be absorbed, which is an endothermic process. When heat and energy is absorbed, going the opposite way, going from gas to liquid to solid, we need to release all that energy. And those are exothermic processes. It also takes a lot more energy, as we've talked about in this chapter, I think later chapters as well, again, to do this transition going from liquid to gas than it does obviously going from solid to freezing or solid to liquid, as it takes a lot more energy to get everybody separated into the gas phase. So a lot more energy required to do that. Any question on phases, transitions, or anything like that? In addition, in this chapter, we also talked about some other stuff. We talked about pure substances. And remember, a pure substance is really just one thing by itself, like water is a pure substance. When we take 2 or more pure substances and put them together, we get what are known as mixtures. And mixtures are a combination of 2 or more pure substances. The important part is that they do retain their identity. So even though they may not look like they're still there, they are still there in their original form. So when we take something known as a homogeneous mixture, that is basically when everything looks the same throughout. So that would be an example of if we took water and some sodium chloride, we would get a salt solution, right? And obviously salt water looks exactly like water, right? All the salt's going to dissolve, but the salt is still there in its original form, but it all looks like one layer. And that is different than a heterogeneous mixture, where you do see different layers in the mixture, even if you mix it for as much as you want. So if you took some water and sand, once again, you can mix that all day. You will still be able to see the sand in there. And that is a heterogeneous mixture. Now, again, no matter what type of mixture that you got going on there, homogeneous or heterogeneous, you can separate out the components by some type of physical means. So you could heat it, you could freeze it, you could boil it, whatever you want to do to it. You can always separate them out by some type of physical means and get both of those things back. Two very common ways that we could separate out mixtures. We did a couple of them sort of in lab this semester. We obviously could use filtration, right? Filtration obviously is where we can take like a funnel, probably something underneath our broken funnel there, and put some filter paper in there. And obviously a filtration is a great way to separate out a solid from a liquid. Obviously, if we took our sand or something like that, the solid would end up on the filter paper, and obviously our liquid would go through. So if we took our sand and water, like I said, we would end up with the sand on the filter paper, the water would go through, and we've now separated out those guys into their original components. You could also do something like distillation. And that's where, you know, for example, you have sort of a closed system and a true distillation sort of deal. And again, if you had some type of salt water, which is a homogeneous mixture, you can start to heat it up. As you heat it up, the water component is going to go off into basically steam. And usually this tube right here that connects it is really, really cold. So when that steam hits the really coldness, it then goes through condensation and drips out on the other side. You obviously could continue to heat the left-hand side until you evaporated off all the water, and you will be left with just a residue of salt that's over there. And once again, we were able to separate out both of the components of this mixture. Even something like a homogeneous mixture, which you can't see the different components, can be separated out through this process. In lab, we did just a kind of simple version of this. You took your evaporating dish, right, and you put your salt water on it. You heated it up. And the same thing happened, except that basically the water was just lost to the environment there. We didn't collect the water. And then what you were left with, obviously, in your evaporating dish, when it was all said and done, was your salt that was there. Hopefully still on your ring there, so it don't fall. Any questions on filtration, distillation, different phases there? We also, I think, around this chapter as well, talked about the idea between chemical changes and physical changes. So obviously, making of a mixture is a physical change, while some type of chemical reaction is a chemical change. Question? Okay. So a chemical change is one where what we start with and end with are fundamentally different substances. So basically a chemical reaction has taken place. So if you took some iron plus some oxygen and a little bit of moisture, you will get iron 3 oxide, which looks like this, where the iron and the oxygen are together, basically rust. You can do anything you want to rust, but you won't be able to get back the iron metal and the oxygen back. And that is different than a physical change where what we start with and what we end with are fundamentally the same thing. Yeah. Yeah.
What I'm trying to understand is like what when I start with usually distilled water and whatever I'm putting in there, and I heat it and then I run it through the thing, you know.
Yeah.
And I got the condensation that drips to the other side.
Yeah.
Is what I'm ending up with different than what's still in the initial start with?
So if you're asking, the important part about a mixture, which I think is your question, the important part about a mixture is actually, even though it may not appear to you that both of those things are in there, you know, in their original form, they haven't fundamentally changed anything. So it's a physical change. So when you look at something like salt water, it just appears to be water to you, obviously, right? It just looks like water. But really the salt's still in there. It's just surrounded by a ton of waters that you can't visually still see it. And that's why in this process, when we heat it, we are able to separate out the liquid water part on one side, and we'll eventually end up with really the salt on the other side, which will be like wet. And, and if you let that salt really dry back out, it'll be just like it was, when you took it out of the shaker or whatever you got it from. So you can get both of those components back. So fundamentally, the two parts of that mixture is fundamentally the exact same things you get at the end. And that's the important part of it. And that's really what a mixture is, and that's why it's a physical change, even though sometimes it doesn't appear that, it appears like something happened, some reaction happened, but really no reaction happened. It's still fundamentally still the same things. It just visually looks different to you in that sort of mixture form. But fundamentally, they're still the same thing. For example, sodium chloride, what you started with in the mixture, and sodium chloride at the end, they're both the exact same thing. And the water obviously is the same as well. Yep. Other questions? So that is really what a physical change is what you start with and what you end with are fundamentally the same thing. So as we were just talking about, obviously, if we had salt water, which is like sodium chloride plus water together in the version of salt water, again, it looks like it's one thing and just salt's not there, but it really is the same as when we took the sodium chloride plus the water to begin with. It is still fundamentally the exact same things on both sides. They just may look different when you put them together. So very common sort of physical changes, as we talked about, are changes of state. So when we go from solid to liquid to gas, that's a very common physical type change. So the common example of that is also water. So when we have an ice cube and then we to liquid water, and then we take the water and heat it up to make pasta, and we create steam. Steam that comes off as it starts to boil is still fundamentally H2O. They just, in terms of how they look, and that's really what a physical change is you haven't really changed anything, you haven't had any type of chemical occur, but what you've changed is maybe the appearance of it or something like that, but it's still fundamentally the exact same things. Okay, so I think that was pretty much everything there in chapter 3. Any questions on any of that stuff there? All right, then we rolled to chapter 10. We went ahead in the book, I think. And chapter 10, I believe, was all about energy, I believe, in this chapter. So this was obviously about energy. And in this chapter, we obviously focused in a lot on two types of processes, which we talked about just a second ago. Obviously, our exothermic, where we release energy, and endothermic, where energy is absorbed. We also talked about in this chapter what are referred to as energy diagrams. Where we have reactants and products, and two of them that sort of look like, if I draw it correctly there you go, reactants and products here in terms of energy. This would be the progress of the reaction heading in this way. So when we look at energy diagrams like this may be drawn better than these, but when we have a situation where our reactants are higher in energy than our products, in order for our reactants really to get down in energy to our products, that would be an exothermic reaction. Energy has to be released. So this would be our exothermic sort of diagram. Opposite is true here, where our reactants are actually lower in energy than our products. That would be an endothermic reaction. Remember that all reactions have a hill that they have to climb, and that hill is right here from the reactants to sort of the peak of the heel. That is what is referred to as the activation energy. And the activation energy is the minimum amount of energy required for a reaction to take place. For a reaction actually to take place, you do need two things to happen, as we talked about. You need a collision, and they need to hit each other sort of in the correct spots on both molecules. And you need them to hit each other with sort of the right amount of energy for this reaction to occur, and that is the activation energy. We also, I think, touched upon at the very top of the hill, which is the sort of most unstable part of it because it's highest in energy. This guy is what is known as the transition state. And the transition state is, as this reactant progresses, you're going to start breaking bonds and start making bonds as you kind of go up. So you're going to be breaking and then making bonds. And up there at the very top is you usually have something there, which is sometimes referred to as the transition state complex. And that is like a substance that has some partially broken bonds, some partially made bonds. It's a very unstable sort of situation, which is why it's at the peak of the energy. So that doesn't usually hang around very long, and it will kind of drop down to the other side there to make products at that point. Now, obviously, the heel for exothermic versus endothermic will determine how fast the reaction will happen in terms of that activation energy. So larger the hill, slower the reaction usually, and sort of the smaller the hill, the faster the reaction will take place. We also talked about one way that you could kind of speed up a reaction is to add a catalyst. You could add a catalyst. And remember that a catalyst is not a reactant nor a product, and it doesn't get used up in a reaction. The whole point of it is basically to find an alternative pathway, and it ultimately will lower the activation energy. So it lowers the activation energy, E of A. And by lowering that activation energy, it allows more reactants to get to the other side, and thus usually your reaction will occur a lot faster. Catalysts are oftentimes written on top of the arrow, like platinum, or may say H plus or something like that. But it just finds an alternative pathway where the reactants are maybe to it, and that allows everybody to come together a lot faster than the catalyst wasn't there, and they're just kind of floating around trying to find each other. It is able to sort of speed up that reaction by doing so. Any questions on that there? Now, in terms of exothermic and endothermic, we talked about a couple of different sort of measurements of energy. One is what is known as the enthalpy, which is delta H, is the enthalpy. And the enthalpy of a reaction is, you can think of it as sort of the heat of a reaction. And the change in enthalpy is calculated by taking the enthalpy of our products minus the enthalpy of our reactants. And on our little diagram there that we were just looking at, that really is really the difference between where the reactants and the products end in energy. So that difference right there would be the delta H between the energy of the reactants and the energy to products. Over here, it would be over here. This difference here would be the delta H value for that reaction. Again, the difference in the energy of where we kind of begin and where we end. Enthalpy and energy is one of those state functions I think we also might have talked about, where it's really the two important things is that where you start and where you end, and where you end in a chemical reaction is the reactant. So that's why when we take the difference between those, we get that energy for the reaction. It doesn't matter if it takes like 40 different steps to get there, or it takes 3 steps to get there, or 1 step to get there. The two most important things in sort of a state function is just that, where you begin and where you end. In terms of values, delta H is usually a negative value for anything that is exothermic. and delta H is usually a positive value for anything that is endothermic. So if you're ever given a reaction and a delta H value, or you calculate the delta H value and you end up with a negative number, it means it's a negative reaction overall. And if you end up with a positive number, it is a thermic reaction overall. And those are good things to remember, because a lot of times the way that sort of reactions are sort of displayed to you in terms of exothermic and endothermic is they just lay up a delta H value for you. And again, and the number really doesn't matter. The sign of it actually does matter when we talk about this. Now, we also talk more chapter specifically about specific heat was in this chapter. And the specific heat, or the specific heat capacity, is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And that's why specific heat capacities have 3 different units. We oftentimes remembered our favorite one, which is the specific heat capacity of liquid water, which is 4.184 joules per gram per degree Celsius. That is the definition, the amount of energy, joules, required to raise 1 gram of a substance by 1 degree Celsius. So that is really why it has all 3 of those units there. Also for water, it is sometimes given in calories, which is 1 calorie per gram per degree Celsius. And the conversion between calories and joules is that conversion right there. 1 calorie is 4.184 joules. Remember that sort of lowercase calories is the one we're talking about here. Uppercase calories with a capital C is sort of nutritional calories. So that's 1,000 of the little guys, or 1 kilocalorie is sometimes used. There's an equation that we use for specific heat, and it is this one here. Q is equal to ms delta T. Q is our heat, our energy, and it has units usually of joules or calories. M is the mass, which has units usually of grams. S is our specific heat capacity, which has units of specific heat capacity, units of joules per gram per degree Celsius, or calories per gram per degree Celsius. And obviously our change in temperature here is our final temperature minus our initial temperature. And one of the very few things in chemistry where we actually do keep the temperature here in Celsius, because the specific heat capacities are usually given to us in Celsius as well. We use the specific heat equation here, as we talked about, whenever you're trying to figure out how much heat is either being given off or absorbed by a substance as you change the temperature. The key part here is the substance stays in the same phase throughout the whole change. So if we took liquid water from 50 degrees to 40 degrees, it is still liquid water in that whole change. We would use this equation to figure out how much heat is associated with it. When you look up the specific heat capacity, it's important to not only find the substance that you're looking for, but to make sure it's in the correct phase. So water is a very common one people mess up with. Water, liquid water is 4.184. Again, if you had water as steam, it's like 2 joules per gram per degree Celsius. And if you had water in the ice form, it's also about 2-ish, a little bit more joules per gram per degree Celsius. So you want to make sure that you are picking the correct one, not only in the substance, but also the phase. The important part here is actually the temperature. It is the temperature that will allow you to either end up with a negative or positive number, as the mass and the specific heat capacity are both positive values. So if our final temperature is less than our initial temperature, that means the energy for that guy has been released, right? And that's the only way the temperature comes down. The substance gives off its energy. The temperature reflects that by coming down in temperature. And that will give us actually a delta T that is negative, and will give us a Q that is negative. And that's important because when we get a Q value that is negative, it is a exothermic process. heat and energy being given off. And when we get a Q value that is positive, it is an endothermic process, which means heat and energy is being absorbed. And that happens when they gain energy, the temperature reflects that by going up, right? And when we take our final temperature minus our initial, we will get a positive number. So it's really important to always do final minus initial, because that's really going to allow you to figure out whether it's exothermic or endothermic and give you the proper sign in that particular case. Any questions on that there? It won't. It will just get it there quicker. So that reaction will give off a certain amount of energy regardless. I guess, yeah. Other questions? Now, if you actually do an experiment like this under constant pressure, which is most cases, the Q that you get will actually be the same as the delta H value for that reaction. So if you do a process under, constant pressure, like the experiment we actually did when we took the coffee cups, right? You could use coffee cups like we did in that experiment and a thermometer basically, and you can do an experiment like this. And very often in specific heat, we follow the change that occurs with water because we know a lot about water and we could relate it to the substance that we're looking at. Remember that heat transfers from hot to cold, right? So the hot guy gets cooler, the cold guy gets warmer as we do that. There's also the idea of what we talked about with this, of that sort of perfect transfer of energy. So again, if we did have sort of some water here at a starting temperature, say at 25 degrees Celsius, and we took a piece of metal here and we heated it up, say like 90 degrees Celsius. Again, kind of like what you did in lab. I think you had your big test tube, right? You filled it with a bunch of metal, right? And you heated it up in some boiling water. If you dump that metal obviously into the water, all the heat for the metal in this case, which is hotter, is going to be transferred to the water. What we would see for the metal is it will cool down, water will heat up, and with the metal in there, right, the final temperature of the metal will equal the final temperature of the water. So if you remember, we can do sort of our specific heat equation for the water because we will have all that information. And there is a relationship where Q of the metal will equal negative Q of the water. So if we were to do in this situation Q for the water, we would end up with a positive number because it absorbed all the energy. That means that the metal would end up with a negative number for Q. It's the exact same number. It's just a different sign because it will be exothermic in this case for the metal. So remember, we did a bunch of calculations. I think in the experiment we did was something like this. Any questions on that there? And again, you can put it all together and do it all one calculation, but sometimes it's easier just to do the water part first and then go back to the metal. And usually in a calculation like this, you're looking for maybe a final temperature of the metal or maybe the specific heat capacity of the metal in this situation. Any questions on specific heat here? I think the last thing we talked about in this chapter, if I am not mistaken, is our friend Hess's law. And Hess's law is that idea of delta H being really a state function. And basically Hess's law is when we have a bunch of reactions like, A plus B, whoops, goes to C plus D with a delta H of like plus 100. Then we have maybe like, C plus D goes to E plus F. Delta H equals minus, shouldn't do that, I would do minus 50 kilojoules. So if we had an equation where, we wanted to figure out what the EF, no, I'm just gonna spell my name, now, E plus F goes to A plus B in this case. If we had a reaction where, hey, we wanted to figure out what is the delta H of this reaction using basically these reactions to do it, this Hess's law is where we take a bunch of little reactions, kind of move them around and change them up and put them together to build an overall reaction. In this case, what we would need to do is is we clearly see E, which is in this reaction here, and it's on the wrong side, so we need to reverse it. And that would mean we need to flip around the bottom reaction to this. Remember that when we flip a reaction or reverse a reaction, the sign of the delta H changes. So in this case, it would go from minus 50 to plus 50. We would also need to actually reverse the top equation. So if I do that, we will end up like this. I would also need to flip the sign on that guy, which would make it 100 kilojoules. If I did this correctly, we could add these equations together. Anything on opposite sides of the arrow will cancel. So the C's are on opposite sides, the D's will cancel. And it will, in fact, give us the equation that we're looking for. In this case, to figure out the delta H at this point, now that I have adjusted my values here, I just add them together, and in this case would give a minus 50 kilojoules would be the delta H for this one. So you may have 2 reactions, 3 reactions, but you want to kind of manipulate them and move them around until you get the overall reaction you're looking for. And then you just simply add up the delta H values for everything that you adjusted. So the way that we can manipulate these equations is pretty much like this. We can obviously, if we reverse it, the sign changes. If we need to multiply by a common number, you would also multiply the delta H by that number. So for example, if I needed, say, 2 of the top guy, I would have to multiply this entire thing by 2. And then I would also need to multiply the delta H value by 2 as well. And lastly, the last thing that you could do is divide by a common number. So if you need to divide by a common number, you would actually divide the delta H by that number as well. So, you know, if I had to again go back through here and divide everybody by 2, I would divide this guy by 2 as well. So those are the 3 ways that you can manipulate sort of these delta H reactions. If you reverse it, change the sign. If you need to multiply the delta H by that same number. And if you need to divide everybody by a common number, then you would divide the delta H by a common number. Any question on Hess's law there? Okay, so I think that is chapter 10, if I'm not mistaken on that. We then went to exam 2 and chapter 4, I think, here. So chapter 4 was our basically the atom basically here in chapter 4. So this was like the atom. So we opened up chapter 4 talking about important experiments that led to the structure of the atom. So to highlight those, right, we had our friend Thomson, who did a little CRT action there. We also had our guy Milligan, who did some oil drop experiment. Remember, from both of these, basically the mass of the electron was determined. This also led to an early model of the atom, which was one by Thomson, which was the plum pudding model. And that was a model where basically we had positive charge kind of spread out through the sphere. We had electrons that were embedded inside. And it was believed that most of the mass of the atom was made up of the electrons. Also before this, right, we had our good friend Dalton and his atomic theory, right? And most importantly, Dalton went bowling on Thursday. There we go. So that probably will be there on the final. So this was sort of the accepted model of the atom. And it was accepted until really the main sort of experiment that really changed most things, which was the gold foil experiment. And the gold foil experiment was done by a guy named Rutherford. And Rutherford basically took alpha particles which are really positively charged radioactive particles. They basically shot them at pieces of gold foil. And basically what he thought would happen in this case, because of the early model here of the atom, because he's shooting these sort of positive guys at it, and it's all positive sort of spread out over that, he anticipated that the alpha particles would go through, but there would be some deflection that would occur because of positive and positive, right? Don't want to be near each other, so they'll reflect a little bit. But he was a little bit surprised. He saw that most of the particles went through with no deflection, which basically meant it had to pretty much hit nothing. It had hit empty space, basically. He did see that every so often they were scattered at large angles. So this was really sort of surprising to him. What he found was basically, most of them just, sell through, no problem. But every so often we see these alpha particles really sort of bounce off at these really large angles. They would even come back to sort of the source as well. So what that meant was he had to sort of move away from the model there of the atom here, the early model, and sort of do away with it and come up with sort of a new model of the atom where the atom is mostly empty space. And that accounts for why most of them just sell through with no problem. It also has a very dense positive core, which is known as the nucleus. That also accounts for why those particles were scattered at really large angles, because positive and positive hit something very, very densely positive, going to make it do so. And lastly, that most of the mass of the atom is the nucleus. So this is really sort of our modern version of the atom, where basically in our nucleus here, we have two particles, which are protons, which are positively charged, and we have neutrons, which have no charge. Out from the nucleus at some distance in that empty space, we have our electrons traveling sort of randomly about it. And this does make sense because out of our three subatomic particles, it is actually the neutrons, which was discovered like in the 1930s, is actually the heaviest, followed very closely by the protons, and it's actually the electrons that is the lightest of the three subatomic particles. And obviously our protons has a positive one charge, a negative one, and obviously no charge there for our neutrons. Question on the structure there of the atom. Let's see what else was in that chapter there. We then talked about some properties of atoms in this chapter, and those were the atomic number and the mass number. The atomic number is the number of protons in an atom, and that can be found on the periodic table, right? And that is the number when we look on the periodic table above the symbol. That is our atomic number there that we find. The mass number, which is sometimes abbreviated as an A, this guy is sometimes abbreviated as a Z, and this guy is sometimes an A, is the number of protons plus the number of neutrons Can we find the mass number on the periodic table? We cannot. So the mass number is not found on the periodic table. What we can do with both of these numbers, if we do have it, is use them to figure out the number of neutrons. And number of neutrons would be our mass number minus our atomic number. And it's important to remember that all those things, right? The mass number, the atomic number, the number of protons, number of electrons, and number of neutrons are all positive whole numbers. So they all should be positive whole numbers, which obviously is why the bottom number that we see on the periodic table is the atomic mass, right? And not the mass number. And if you look at their, they're pretty much all decimals on the bottom there. Also, what we do see, though, is that it is the atomic number, or the number of protons, which is the most important in determining the element we're talking about. No element has the same atomic number, which means if you do know the atomic number or you know the number of protons, you pretty much could just go to a periodic table and figure out what element you're talking about, because, again, nobody shares the same atomic number. We also can write these guys in sort of their isotope form. Isotopes are the same element, but have different numbers of neutrons. And up on top of the symbol on the left there goes the mass number. Bottom left there goes the atomic number, right? And typically we take the top number minus the bottom number will give you, obviously, the number of neutrons. Every element has protons, electrons, and neutrons except for hydrogen. Hydrogen does not have any neutrons. It has a proton and electron. So everybody else has all three, just hydrogen does not. If we did have something with a charge, you know, so if we took something like nitrogen here and do a 7, and we'll do a 13 versus nitrogen with no charge here. For our nitrogen with no charge, the atomic number, which is the bottom, would tell us it has 7 protons. And because it has no charge here, it would also need to have a matching number of electrons to balance it out to 0. Taking our neutrons would be 13 minus 7. I think that's a 6 in that case. When we do get something with a charge, our number of protons here for this guy would still be 7. Again, we cannot change the protons, otherwise we use the element. But in this case, it has a -3 charge, which is an anion. Minus means it gained electrons. 3 is how many it gained, which means it actually, in this case, would have 10 electrons. 10 negatives and 7 positives leaves us 3 negatives overall. And our number of neutrons here would obviously still be 6 in this case. Question on that. So if something has a negative charge, it means it gained electrons, which is why it's negative. And the only thing that would change is the number of electrons. And obviously, if it has a positive charge, which is a cation, it has lost electrons. So again, the only thing that would change would be the electrons. It will go down from its neutral guy. Any questions on that there? Okay. So we talked about that. Also in this chapter, we hit the favorite periodic table, right? So we talked about the periodic table here. And we talked obviously about groups. So 1, 2, we'll go 3, 4, 5, 6, 7, and 8. So when we do the periodic table, we do the representative numbering there, which again is group 1, group 2, skip the middle, 3, 4, 5, 6, 7, 8. We also have in the middle there between group 2 and 3 is our transition metals. We also have like a staircase that kind of comes down this way. To the left of the staircase, these are all metals. To the upper right of the staircase, those are non-metals. and the staircase itself, those guys that make up the staircase, are what are referred to as semi-metals or metalloids. And the one exception is on most periodic tables. I'll just write it. Actually, I'll go above here. Hydrogen, right? Hydrogen is a non-metal. And again, even though it's above group 1, it is not part of group 1 because group 1 is metals. So hydrogen is sort of an exception to that. Groups go up and down, right? And periods go left to right across the periodic table there. Certain groups here obviously have special names. So group 1 there is the alkali metals. Group 2 is the alkaline earth metals. Group 7 is our halogens. And group 8 is our noble gases, I believe there. In addition, most periodic tables down here where I wrote the PT have 2 sort of rows on the bottom, and those guys again, kind of go in this area here, and those are sometimes referred to as the lactonized and actinide series, again because those are the elements they should follow on the periodic table. They're also sometimes referred to as intertransition metals because they technically go in the transition metal region. Metals have good conductor of heat and electricity. They're usually shiny. They could be pulled into wires. Non-metals are sort of the opposite. They are dull, they are brittle, they're bad conductors of heat and electricity. And our semi-metals there basically kind of fall on both sides of the spectrum there. The same semi-metal can be, some properties are very much like metals and also have properties are very much like non-metals. And that sort of makes sense as you see sort of their location. They are in that transitioning of going from metals to non-metals as you go across the periodic table. Any questions on the periodic table? Yes. Has malleability. Yeah. Yep. Other questions on that? I think as well, we sort of officially first talked about in this chapter at the very end, ions and sort of the electrical nature of matter. Ions obviously are guys that have charges. We have our cation, which is positively charged, usually a result of losing electrons. We have our anion, which is negatively charged, a result of gaining electrons. And electrolytes are solutions that can conduct electricity because of the presence of ions. And there are strong electrolytes which will 100% break apart into ions. And they're really good conductors of electricity. So for example, hydrochloric acid is an example of that. All strong acids are 100% breaks apart into H+ and Cl-. So in solution, 100%, this is what you have. None of the HCl units still together. There's also weak electrolytes that mainly stay together. But will produce some ions. So HF is an example of that, which is a weak acid. In solution, it will produce a few of these ions, but will mainly stay together. So it's still able to conduct electricity because it does produce a few ions, but nowhere near obviously something that's a strong electrolyte. And then obviously we have non-electrolytes, which will dissolve in solution, but they will not produce any ions. So since they don't produce ions, they will not conduct electricity. Any questions on that there? I think that was chapter 4. Any questions on chapter 4 here? Not too bad. Okay, then let's see here. We went to, after that, something. We went to chapter 11 after that, I believe. So chapter 11, it's really all about electrons. We talked a lot about in this chapter. We did open up with the idea of waves, and sort of its relationship to energy. A wave obviously looks something like this, where we do have what is sometimes referred to as lambda. I could draw that right there, lambda, which is the wavelength. We also talked about the frequency, which is sometimes referred to this. And the speed of light, which is c, which is 3 times 10 to the 8 meters per second here. And c is equal to the wavelength times the frequency. And there is a relationship to energy, which is the energy is equal to h times the frequency. H is Planck's constant, which is 6.63 times 10 to the minus 34 joules seconds, which if we substitute those guys in together, gives us hc over the wavelengths. Frequency, wavelength. So these are some equations, and truthfully, if I remember correctly, we didn't really do any calculations with these, but these are some of the equations that go with the waves, so you don't have to really worry about too much of those. But what we did talk in terms of relationship between waves and energy is if you have a wave that has a very short wavelength, it typically will have a high frequency, and that usually results in high energy. So things with very short wavelengths have high frequency and high energy, as opposed to something with a much sort of longer wavelength here. So if we have a longer wavelength, we have a lower frequency, and that usually results in a lower energy in that case. The waves are really important because what we really talk about mostly in this chapter is the idea of electrons transitioning from different energy levels, and they will give off energy in the form of a wave. And obviously, if it's a shorter wavelength, will be higher in energy, longer wavelength will be lower in energy. And depending on what the wavelength is for that particular wave, it may be in something like the part of the spectrum where we see colors and things of that nature. Any questions on that there? All right, so we will pause here for now.